We live in a major spiral galaxy that we call the Milky Way. It's home to the Sun and a few 100 billion other stars. The galaxy belongs, in turn, to a cluster of galaxies. Astronomers call it the local group. And the local group is part of the Virgo supercluster, an archipelago of galaxies stretching across 100 million light-years of space. The galaxies are marching away from one another as the universe expands. In a computer simulation, based upon astronomical observations, we witness something never before seen by human eyes: the predicted scattering of the Virgo supercluster by the expansion of the universe over the course of the next 50 billion years. The expansion of the universe was predicted by Einstein's general theory of relativity, published in 1915. But the idea seemed so outlandish that Einstein himself rejected it. He introduced an extraneous term into the field equations to try to make his theoretical universe stand still. Later, Einstein would call this modification of the theory the worst blunder of my career. Then, in 1929, the American astronomer Edwin Hubble, without knowing of the relativity prediction, discovered that the universe is indeed expanding. Einstein and Hubble met in California in 1931 and celebrated Hubble's having found at the telescope what the mind of Einstein had conceived. Astronomer Alan Sandage, once Hubble's pupil, has devoted much of his career to studying the expansion of the universe.
It is not as if these galaxies are expanding into a space that's already there. The view is that the space itself is expanding, carrying the galaxies with it. The expansion creates the space. It's, well, the crucial analogy first made by Eddington as long ago as 1930, just 1 year after Hubble had announced the expansion, was you can conceptualize the thing as the two-dimensional analog by the surface of a balloon. You paint dots on the surface of a balloon and you blow it up. You put yourself on any dot, you seem to be the center, and all the other dots move away from you. Now take the air out of the balloon and look what the dots do. All the dots come toward every other dot, and if you could take all of the air out of a perfect balloon, the surface itself would go to zero. All the dots would be back at one place at one time. Every place is the center of the expansion. When you talk about this, the question that always comes, well, can you find the center of the expansion? Every place is the center of the expansion. There is no center to the beginning. Everything was back at one place, and every place and every time was identical in the beginning.
Palomar Observatory in Southern California.
Sitting inside a time machine of sorts, an instrument capable of looking directly into the past. Down at the bottom of the tube, far below me, there's a curved, polished mirror that can gather as much starlight as all the eyes in a community of 20,000 people. That light is brought here to a single intense focus, and through that tiny window, one can peer out for billions of light years in space and look back for billions of years into cosmic history. can harvest some pretty old light with a telescope as large as the 200-inch reflector at Palomar. This image just coming in now is of a galaxy 40 million light years away. That means we're seeing it the way it looked 40 million years ago, which is a long time, but it's only a fraction of 1% of the time that's elapsed since the beginning of the expansion of the universe. If we were to plot our place in cosmic history, we might make a line representing time, starting with the Big Bang, the beginning of time as best we can understand it, and stretching down some 15 billion years or so to the present day. Here we are in a galaxy today, and we could have the vertical axis represent space. Now we can only see those events, the light from which, traveling through space, has had time to reach us. And we can designate this by drawing what the scientists call a light cone. The angle of the sides of the cone is defined by the velocity of light, the fastest way we know of that information can travel. A galaxy like this, at 40 million light years away, is right here in our own neighborhood. And pretty much all the other galaxies that we can see clearly lie quite close by on the cosmological scheme of things. If we look further out, the galaxies begin to get pretty dim. Let's see if we can get a cluster of galaxies here. Each of those tiny little fuzzy dots, so small that you may find it difficult to see them, each of those dots is a sovereign galaxy of about 100 billion or so stars and untold numbers of planets. But the galaxies are so far away that existing telescopes, even the 200-inch at Palomar, can't make them out very clearly. The greatest distance to which we can see galaxies at the absolute maximum is half of the lifetime of the universe ago. Further than that, they're just too dim to be seen with existing telescopes. But fortunately, the early universe appears to have been inhabited by a class of objects called the quasars. The quasars, which may have been the nuclei of young galaxies going through a violent, youthful phase, are so bright, they shine so brilliantly, that we can see them at much greater distances than we can see galaxies. If we can call up an image of a quasar, this one is so far away that its light has been distorted by a galaxy lying between us and the quasar, and the result has been a double image. These two dots are actually of a single quasar, a quasar whose light has been traveling for so long that we see it as it was when the universe was less than 5 billion years old, back when the universe was less than 1/3 its present size and age. The quasars are so bright that thousands of them have been detected with telescopes here on Earth. And in fact, we could see them at even greater distances than we do if there were any. But at very great distances, getting back toward 15 billion years ago, the Palomar telescope and other large telescopes find no more quasars. The explanation seems to be that we're penetrating back to a time when the universe was so young that there hadn't yet been an opportunity for stars and galaxies and quasars to get organized out of the primordial material and to start shining. So way back here, at extremely long times ago, there's an epoch of darkness. And yet, even before that, it's possible to see another form of energy, the energy left over by the explosion that began the expansion of the universe, by the Big Bang itself. This energy permeates the universe, but it's been so thinned out by the cosmic expansion that it's shifted down from the wavelengths of visual light into the radio spectrum. And this cosmic background radiation, as it's called, can be detected using a sophisticated radio telescope, or, as chance would have it, by using an ordinary television set.
Any TV set hooked up to an antenna can detect the ancient photons from the cosmic background radiation. To see them, turn down the brightness control and tune the set to an empty channel. Not right now, hopefully, but after the show. And about 1% of the specks of snow that you'll see on the screen are photons left over from the Big Bang itself. They're relics of the infancy of the universe, particles that have been hurtling through space since before the first stars and galaxies were born. The legacy of the Big Bang is still with us. The heat released by the sun and other stars represents a fraction of the energy stored in the nuclei of atoms at the outset of time. It was then, when the universe was still bathed in fire, that nature would have worked in the marvelously simple way glimpsed through the unified theories.